2024. I'm Danny He, and today with me is Dongxue Zhang, VRTAs for today's lecture, topics about AI for buildings and cities. Climate Change AI is a global nonprofit that catalyzes impact work at the intersection of climate change and machine learning. For more information, please visit our website. So for today, we are gonna have 2 lectures. Each one will last 1 hour. The first lecture is about role of data and AI for climate change mitigation and adaptation in cities. The speaker of the lecture is Professor Andrew Hsu. So Dr. Hsu is an associate professor of public policy and the environment at the University of North Carolina, Chapel Hill. She is a founder and director of the Data-Driven Environment Lab, which applies data-driven approaches to pressing environment issues. Her research explores the intersection of science and policy and the use of data-driven approaches to understand environment sustainability, particularly in the area of climate change and energy, urbanization, and also air quality. So welcome Dr. Hsu to give us presentation.
Are you ready for me now? Okay, thank you. Great. Thank you so much, Downling, for that really awesome introduction and that very old photo from when I was a PhD student. So hopefully I can be half as energetic as that photo. Okay, so I'm going to share my slides, and hopefully I was having some technical issues earlier, so hopefully this goes smoothly.
Sure.
Okay, and then can you see, or tell me what you can see?
Yeah, okay.
Can you see the presentation, or is it something else?
Yeah, we can see the presentation.
Okay, and it's full screen. It's not split or anything weird?
It's full screen.
Okay, perfect. I wanted to start my presentation today, and we're very lucky to have a good friend of mine, Filip Biljecki, to give a presentation on buildings. So I'm not going to cover anything about buildings, but really give more of a broad overview of the role of data and AI for addressing climate change, both from the mitigation angle and also the adaptation angle in cities. I wanted to start first with a poll question. I've been told that you have access to this poll, but I want to know, from your opinion, which area do you think AI can best help cities? So A would be identifying emissions hotspots and areas for reducing those emissions. B would be characterizing risks and vulnerabilities within urban areas. C would be comparing best practices for managing climate change. And D, improve planning for transportation or waste-related emissions or something sector-specific related to cities. So I'll give you just a minute. There's no right or wrong answer, just really want to see what the feeling is in the room. And I'm assuming once people respond, we'll be able to see the results. Okay, this is great. Wow, so we have a lot of planners in the room. A lot of responses for D, improve planning for transportation, waste-related emissions. And so it's interesting because I'll show some research that reinforces at least the transport part. And then B came in second, so characterizing risk and vulnerability within urban areas. That's great because I'll also present a case study along those lines. And then A and C, I also have some case studies on those topics, but less responses. Okay, well, thanks everyone for responding to the poll. So hopefully that gets you started to think about what the opportunities might be for data and AI to address particular climate-related issues in cities. So in my very short 45 minutes, this is an overview of what I hope to cover. First of all, I want to just give you a broad overview of cities and the climate crisis. And then I want to turn to specifically talking about some of the data challenges within cities related to climate change. I'll then move into talking about a case study related to how we can apply AI to address some of these data challenges for mitigation in cities, and then talk about adaptation, which I'm less expert and versed in, but I do have some work that is characterizing at least heat exposure and heat risk within cities and urban environments that uses machine learning and AI. And last, I want to talk about some challenges. So cities and the climate crisis. Many of you may be familiar with this figure here, which is illustrating the Great Acceleration, or the period where humans have now become the dominant influence on the environment, on ecosystems, on our atmosphere and our climate. And that's been referred to by researchers, including Will Steffen, who recently passed, called the Great Acceleration. So you can see that on the left, since the Industrial Revolution occurred, we've seen almost exponential increases in population, in GDP, foreign direct investment, urban population. More than half of the world is now living in urban areas and cities. Primary energy use, all of these, you can see these orange curves here are almost all universally increasing and accelerating at an exponential pace. On the right, at the same time, we can see worrying trends, including increases in carbon dioxide and other greenhouse gas emissions like nitrous oxide, methane, stratospheric ozone, surface temperature, ocean acidification. They too have also been accelerating as we see these other socioeconomic and demographic trends of urban population and GDP and foreign direct investment also increase. And what that has also meant is that cities are also contributing to this great acceleration and this transformation in the natural environment and also in the atmosphere. So these are some statistics that the UN Habitat put together for one of their UN Habitat annual summits. And you can see that even though cities occupy less than 2% of global land area, what it translates into, and there's some debate in terms of the exact figures, and so that's why I have these greater than, but it's assessed that cities contribute to about 70% of global GDP and consume about 60% of global energy. They also generate around 70% of greenhouse gas emissions. I've seen that number as high as 85%, and they're also responsible for about 70% of global waste. So let's dive into the green circle in terms of how cities contribute to greenhouse gas emissions. So this paper, or this figure, was adapted from a paper by Karen Cito and myself and some other colleagues who study cities and the intersection with climate change. And it's a great illustration of the ways that cities contribute to global climate change, both within their immediate administrative boundary, but then also beyond. So you can see in the blue that not only do cities consumption occur within its own boundary, but also cities, they export waste and other goods. And so then there are also carbon flows and greenhouse gas emissions associated with these outflows from a city, but then they also import, as you can also see in this purple arrow here. I don't know if you can see my cursor, but the purple arrow here, they're also importing materials and energy that they consume within the boundary. And then there are also indirect effects you can see in this red dotted line here as well of these consumption patterns and the concentration of activity and humans and urban infrastructure buildings that also can impact climate change as well. So you may have heard of or been familiar with the urban heat island effect, which basically measures the temperature difference between an urban area and its background rural setting. So it essentially measures how much hotter a city is by a function of its built environment. And so you can see in this illustration that the urban heat island has been measured to make cities around 3 to 10 degrees Celsius hotter than in rural area where you have a lot more tree cover, you have a lot of shade, you have grasses, you have a lot more transpiration and water evaporation from the soil. And within a city, obviously with impervious surfaces like asphalt and pavement and concrete and just these built materials within buildings that can trap some of the radiation coming in from the sun, and it makes a city much hotter. And so in these two ways, both in terms of consumption and directly consuming energy and exporting waste, and also co-locating a lot of business activity and having to consume electricity, and also you have transport within a city that generates these greenhouse gas emissions. But then it also, the second dimension where cities are contributing to global climate change, and particularly local climate effects, is through the urban heat island. So the IPCC, the Intergovernmental Panel on Climate Change, which is the largest scientific body that synthesizes information related to climate change, that came out with its first report in the 1990s. And then most recently, the sixth assessment report came out a few years ago, with the synthesis coming out last year. Has a few chapters that synthesize the scientific information related to this relationship between climate change and cities. And so I have a couple of slides that pull out some of the most relevant findings from the IPCC, the latest 6th assessment report, which I contributed to Working Group 3. There were 3 chapters that touched on human settlements and the role of cities in combating climate change. So that would have been chapters 4, 8, and 13 in Working Group 3. And so you can see here just a very nice summary on the left of why cities are the hotspots of global warming. And so in terms of this local effect on temperature, these bars here synthesize the overall warming effect of cities on local temperature. So you can see the city geometry, so that the building density, the city layout, the height of buildings and the size, and also heat from human activity. So heating, but then also you think about air conditioners, and those also can generate heat within an urban environment, and also traffic. Cars also generate a lot of heat, especially if they're not electric cars and use internal combustion engines. And then, of course, building materials. So the asphalt and concrete, those can also trap heat. And then you can see that cities, because they often lack vegetation and water that rural environments might have, or forests or grasslands or grassier areas, then they lack the same amount of water and vegetation that would actually make them cooler. So this is a nice summary. And then you can see here on the right, the trends in global surface air temperature between 1950 and 2018. And cities are some of the hottest areas around the globe. You can see New York and Los Angeles are certainly warmer than their surrounding areas. And so because of the elevated temperatures as a result of the built environment and urban heat island effect, we can see that cities are impacted by climate change, and they're some of the most vulnerable areas on the planet when it comes to climate change impacts. So the second working group of the IPCC is focused on adaptation impacts and or climate change impacts and adaptation responses. And so these are some of the figures that I pulled from Working Group 2 that summarizes the ways in which cities are impacted by climate change. And so coastal cities, there are ocean impacts. So many coastal cities are frankly sinking because of sea level rise, and you have storm surges. And when you have extreme events like hurricanes, those can also lead to flooding in coastal cities. And there are also terrestrial impacts as well. So here on the left, you see erosion, land subsidence, salinization. This is also as a result of cities, a lot of cities being located on the coast. And then atmospheric impacts, so severe storms, tropical cyclones, and then hydrological impacts as well. There can be flooding, increased precipitation that can affect urban environments because, again, there's a lot more impervious surface. So it's not like a rural area where a lot of the rainwater or additional rain and precipitation can just be absorbed by land. It actually then runs off, or it can collect and lead to flooding in urban areas. And so this schematic here, also from Working Group 2, talks about this intersection of these hazards, and then vulnerability, exposure, and responses all intersect to really then inform what the cities then, how they can articulate responses to these risks of climate change. And so I'll talk a little bit about how with data, or you can see here some of the drivers and then the physical impacts, but how data and how we can use data to try to think about measuring different elements of these different dimensions. Because I think one of the punchlines is that climate change is incredibly complex, whether you're talking about mitigation or adaptation. And there are many areas where cities actually need a lot of data to be able to inform the characterization of hazards, but then also formulate strong policy responses. And so that's a great segue into my next slide, which is, well, what can cities actually do about it in terms of contributing to global greenhouse gas emissions, which make temperatures warmer, but then also through its physical built environment, the urban heat island effect leading to local temperature increases. And that has translated into a variety of impacts in terms of sea level rise, more extreme events, drought, heat waves, more precipitation. And so there are really 2 options for cities in terms of what they can do to address these complexities that are posed by climate change. And so one is that they can mitigate, they can reduce their carbon footprint, they can try to reduce some of those emissions and primarily result from transport or from building energy consumption or electricity use. Or they can try to adapt to climate change, which means reducing vulnerability and increasing resilience. And with the way that the global temperature trends are heading, and so if you haven't been reading the news lately, you would have seen that now most climate scientists and folks who are monitoring global temperature data have now established that the world as a whole has already surpassed 1.5 degrees Celsius above pre-industrial levels. And you may think, well, that doesn't seem like it's a lot, but that's really the threshold by which a lot of the climate scientists and the models have shown some irreversible impacts of climate change. And so that includes like sea ice loss, or thinking about the Greenland and the Antarctic ice sheets. So these are some of the irreversible impacts. But now most cities, when we talk about climate change, it's no longer an either or. Should we mitigate or should we adapt? But it's really a recognition, because of these temperature trends and the way a lot of the indicators are in vital signs of climate change are heading, that we have to think about doing both. How do we actually mitigate as quickly as possible so that we can try to shave off any additional increase over that 1.5 degrees Celsius? But then recognizing that climate change impacts are happening and they will become more frequent, more prolonged, and more severe. How do we actually reduce vulnerability and increase resilience? So in the AI field, there has been a lot of research that has been developing into many different aspects of both climate change, adaptation, and mitigation. This is a great paper that I found that summarizes some of the artificial intelligence-based solutions. Of course, addition to CCAI, I encourage you all to go to the wiki. It's an amazing resource that'll get you started in these very many dimensions of climate change mitigation and adaptation, and give you some great example research areas and some data sets, and also some examples and background reading. So definitely encourage you to go there. But also, I think this paper is great at summarizing some of the ways in which AI is addressing some of these dimensions of climate mitigation and adaptation. So for cities, the relevant ones would be energy optimization and managing efficiency of energy consumption within buildings. I'm sure Philip's going to talk about that a lot. And then hopefully in this course, we'll also talk about forest management as well, because that's an area, particularly when we talk about land use emissions, that's really hot. Actually, one of my former students has been working at the World Resources Institute, and they just partnered with Meta to develop a very high resolution data set of trees. And so that's really relevant, because a lot of countries and other entities are looking towards land and forest for carbon sequestration properties as a way to offset some of the emissions from energy sources or other hard to abate sectors that might be difficult for them to completely eliminate from their footprint. And then in terms of grid management, there's been a lot of research on renewable energy forecasting and load management. In agriculture, for precision agriculture, how can we use fewer pesticides? And then on the adaptation side, that's really this in the middle. How can we use AI to ingest large amounts of weather and other types of atmospheric data to develop early warning systems for extreme weather events? And then, the optimizing transport is not adaptation related, but that's also a very hot area that relates to the design of smart and resilient cities for sustainable development. So how can we optimize transport to reduce congestion, and also by way of reducing congestion and optimizing traffic patterns, then reduce air pollution and also reduce energy consumption and fuel consumption that leads to more greenhouse gas emissions. So that's just a very quick overview of the ways in which cities are contributing and are impacted by climate change. Now I want to talk about the data challenge. So I alluded to the fact that in those complex diagrams from Working Group 2 of the IPCC, that there are many different ways in which cities have to think about climate change impacts in order to assess them and then to develop appropriate responses. And so I've been in the space of working at the intersection of science and policy for my entire career. My dissertation was actually focused on how do we actually translate scientific information, and in particular data, into a policy setting. And one of the ways and one of the tools that can allow for this type of translation of science and data into policymaking is through indicators that help to signal to either citizens or policymakers or planners what the extent of the problem is, and then what are some of the driving forces or the pressures or the state of the situation, and then how can we actually measure the impacts and then eventually our responses to address and tackle those problems. So this has been referred to as the DPSIR framework. And this is a diagram from the UN Environment Program, but a lot of international or intergovernmental agencies like OECD and a lot of governments have also adopted this type of framework when they talk about measuring a particular problem and then evaluating the policy response. And I think this is really helpful to help think about all the different potential areas where a policymaker or a civil society group or a program evaluator would want to collect data to then be able to evaluate what's actually going on. So I tried to list areas for mitigation and adaptation that represent types of data that somebody might want to collect if they wanted to assess, for example, what's a driving force behind climate change? And if I wanted to mitigate my carbon footprint or my greenhouse gas footprint, what might be something that I would want to measure? So obviously greenhouse gas emissions would be one of those driving forces for mitigation that I might want to measure. But then for adaptation, that could look really different. Emissions are probably not as relevant or not the most relevant indicator instead of data. So that might be inequality or poverty data, because that certainly shapes people's ability to adapt. I was just talking to a reporter yesterday about heat and heat exposure. And I mentioned how the city of Raleigh is now adapting the trash collection pickup times based on temperatures because they don't want their workers to be exposed to high temperatures. So that's an example of an adaptive response to try to protect workers from the hottest parts of the day by shifting their working sessions. But then to really understand, or inform that particular response, we may want to collect relevant data that would help to understand the pressures. And so that might be temperature, for example, I guess I don't have that listed here for an adaptation response, but for both mitigation and adaptation, spatial data on land use and deforestation could also represent a pressure that would drive then either less shading and within an urban area, or for mitigation, actually reduce some of a city's ability to sequester greenhouse gas emissions. So, I think you'll have access to these slides later, but I think this is a really great way to think about all the different areas where you might want to collect data, or you might need to collect data to really understand the extent of the climate change problem that a city faces, and then areas where AI or machine learning could help fill in some of these gaps. And data gaps have certainly been a consistent theme in the literature and the scientific synthesis related to cities and climate change. So I actually pulled this from the 5th assessment report because some of their conclusions in the executive summary really struck me. And so it's probably too tiny to really read, but I have to try to make it a little bit bigger here. You can see this one paragraph in the executive summary of this chapter. It identifies and highlights a number of key knowledge gaps. So one, and this is all related to human settlements in cities and climate change. So they identify, first, there is a lack of consistent and comparable emissions data at local scales, making it particularly challenging to assess the urban share of global greenhouse gas emissions, as well as develop urban typologies and their emissions pathways. So going back to DSPIR, it's like for mitigation and to inform mitigation responses, we need to know how much cities are contributing to global greenhouse gas emissions. And the IPCC, so these are all the scientists who work very closely on human settlements and urban areas and climate change. And they're saying, we look through all the literature, there's not enough data to really understand how cities are contributing to the problem to begin with. They say, second, there is little understanding of the magnitude of emissions reduction from altering urban form and the emission savings from integrated infrastructure and land use planning. So that comes in the in the DSPR framework. It's like the responses. We have very little evidence of what the effect is of various responses, particularly in terms of spatial planning and infrastructure planning. And then there's an issue with lack of consistency and comparability of local emissions accounting methods. So it makes it really difficult to say New York and LA or London and Paris, how are they all performing when it comes to addressing climate change and mitigating their impact on global climate change, because methodologies are very inconsistent. And then here, fourth, it says there are few evaluations of urban climate action plans and their effectiveness. So when cities decide to tackle climate change mitigation and adaptation, there's very little evidence. Again, this goes into the response area of the DPSIR framework. There's very little evidence of the evaluation of those responses and what is actually effective. And then they say, well, there's more. There's a lot of uncertainty about future urban trajectories. So you can see there's a lot of information and knowledge gaps. So I think this is a really great summary, and I think a charge and a call to action on the part of the research and the data and the AI community to think about how we can potentially use AI to address some of these gaps. So I want to talk about what my group has done and what other research has existed to address some of these gaps. But I thought it's important to just highlight and give you like a very quick overview of some of the challenges that those who are kind of in the weeds of studying cities and climate change are dealing with on a day-to-day basis. And certainly this has inspired some of my own work to try to apply AI to tackle. So to illustrate, I guess, the third and the first gaps, I just want to give you an overview of one of our databases of where we're collecting and compiling and making consistent data for cities that are pledging types of climate action. So cities, they can either come up with their own climate action plan, or they can join a international climate initiative or a network of other cities across boundaries. And so this includes C40 Cities for Climate Leadership. You may have heard about that effort. It was started by former New York City Mayor Michael Bloomberg, or the Global Covenant of Mayors, which has like more than 12,000 members. And what they do within these networks is they say, okay, I sign up, I pledge that I'm going to tackle climate change, and I'm going to publish a plan and maybe an emissions inventory. And so we've now recorded around 13,000 of these cities globally are taking some kind of action on climate change, whether it's mitigation or adaptation, or they're participating in one of these kinds of networks. Now I'm going to show you the same map and how many cities actually report their greenhouse gas emissions data. Only fewer than 10% of them actually publicly report and publish emissions inventories. So that map here, I'll just go back for emphasis. You can see how many cities are pledging climate action across the globe. And then we can take a look at how many where they actually publish regular emissions inventories. Europe, but then in North America, we have actually a lot in Japan, but then the rest of the world, you can see major blank spots. So, and this picture really hasn't improved. Like I've been studying and collecting emissions inventories and this kind of greenhouse gas data from cities for well over a decade. And the picture really has not meaningfully improved, unfortunately. So this is clearly an area where I think that machine learning and AI can really help, particularly in the realm of data fusion. Are there other sources of data where we're not relying on city governments that may not have a lot of capacity, or they may not have a lot of resources or technical know-how to develop these inventories? Because it's expensive, it's time consuming. You have to actually either have direct monitors on top of industrial facilities, on tailpipes of cars, or know how far those cars are driving and applying emissions factors that can then calculate the tons of CO2 per unit of greenhouse gas emitting activity. And that can be really resource intensive. And so cities who regularly report these greenhouse gas inventories, like New York City or London, they have whole teams of hundreds of people who are actually collecting this kind of data and developing these reports. And I've heard very consistently from cities that they have a lot of reporting fatigue, and it's difficult for them to dedicate the same resources to develop these inventories. So I think one way that AI can be really helpful is thinking about data fusion or data integration. So taking data from multiple sources that can include, for example, geospatial data that I have here on this slide. So satellites and satellite remote sensing can help us develop proxies of population and population density. We can also measure power plants and large emitting sources from space. We can also look at air pollutants. So we know that PM 2.5 and NO2 emissions, these come from transport-related emission sources. So we can also use satellites to measure the concentration of these particulates. And then this is the beauty of machine learning and AI. We can take all of this data, all of these globally available data sets for information and data that relate to a city's greenhouse gas footprint, and then put that into a model to then predict what cities' emissions are likely to be, even in the absence of having those self-reported inventories. And so that's exactly what this study did. You can see the underlying time series here of those underlying globally available remote sensing or geospatial-based data sets on fossil fuel sources like power plants and large industrial facilities, air pollution, population, GDP, how much heating is being used by these cities, and then also air pollutants. And that then, because this data you can see is annual, we can then reconstruct using machine learning annual predicted emissions. So what is a city's likely emissions going to be? And you can see that in the case of these three cities, they did report their inventory. So that's in these red triangles here. And I can make that a little bit bigger so you can see Here, this is a city in Belgium. So instead of just having one self-reported data point, we can get more of a sense of its likely emissions from 2001 all the way to 2018. Same thing for Tolosa in Spain, and also for London, UK, even though they did report 2 of their emissions inventories. So this information is much more useful, because if you just have one data point, then I can't measure the impacts and the responses of my DSPIR. I really don't know. I can just measure the state, one data point, right? Like, this is the state of emissions for the city in this particular year. But then with this time series, using machine learning to fill in a lot of these blanks, then I can start to get a sense of the trends. Here for Tolosa and for London, I can see that there's a downward trend of their emissions over time. And that's really useful, because then going back to the IPCC's question about, we don't know the effectiveness of climate actions and climate action plans, you can then start to gather some data to measure at least a directional signal of where emissions are heading for that city. So we can go beyond the cities that just report these few inventories to then really fill in the gaps within all urban areas or all cities within Europe. And so that's what this map here on the right has shown. On the left, these are cities that are participating in a transnational climate initiative called the European Covenant of Mayors for Climate and Energy. That includes, I think now, more than 10,000 European cities that are pledging some type of climate action. And so then we can get more of a sense of their emissions reductions trends. So here we see that 74% of cities have likely reduced emissions versus 53% of those just in general that may not participate. We can also fit these, and I have an example later, we can also fit these into statistical models to try to get more detail in terms of how these emissions reductions trends might relate to actual actions and other activities that cities are actually doing. But this just gives you a look at what the possibilities machine learning and AI open up in terms of filling in some of these data gaps for something as basic as, what are the greenhouse gas emissions of cities? It may seem like a deceivingly simple statistic. I show those 3 bubbles, or there's 4 bubbles from the UN, and the fact that cities contribute greater than 70%. But actually, those numbers are only based on like 6 studies, and many of them were conducted more than a decade ago. So probably fairly out of date. And at this point, we need to update them. And I think machine learning is one area where we can try to fill in a lot of the gaps by allowing for the integration of so many different types of data sets that don't just include self-reported numbers that a city has to then compile itself, but then leveraging the fact that we have Earth observation, satellite remote sensing, geospatial data sets, even volunteered geographic information from citizens and from citizen scientists. All of this data we can now almost very efficiently and seamlessly integrate with the power of machine learning. So before going into the case studies on mitigation and adaptation, I have another poll for you. So in this poll, which area do you think cities have the least data to make climate-related decisions? And again, there's no right or wrong answer. I just want to know your opinion. Is it finance? So how much climate-related actions cost to implement and what the benefits are? B, is it in terms of risks? What climate-related risks are the most urgent and where? C, nature and biodiversity, what nature-based solutions, so we're talking about green space or water or trees that could also help to mitigate the impacts of climate change and make a city more resilient. And then D, policy, how effective policies to mitigate and adapt to climate change are performing. So take a minute to answer this, and then we'll talk about the results. Okay, great. Wow, so pretty even split. And it looks like B slightly nudges ahead. So cities have the least data to make information or climate-related decisions on risks. So what climate-related risks are the most urgent and where? And then also we have policy. So that might have been biased by my own personal experience and discipline. But so policy and also the IPCC identified that as a gap. And then we have nature and biodiversity, what nature-based solutions are available and how nature is being affected by climate. And then lastly, finance. So very interesting. And I think that the results, certainly in my experience and working with a lot of city and urban practitioners, it definitely depends on your perspective. I feel like a lot of city practitioners would probably say all of these, they need data and information on all of them. Or certainly that's what I've heard. But yeah, certainly I think finance is an area where a lot of cities express a lot of concern, because if they want to address climate change, or they want to collect data to know how they can address climate change, it all costs money. So a lot of them are increasingly concerned with how they're going to finance solutions, even if they do have data to then inform a response. And so one thing that's interesting, I just had a conversation with Durham City, which is the city next to mine, and they have a upcoming bond where they're able to think about different sustainability interventions. And so they were asking for advice of where, if they wanted to, for example, implement cool pavement initiatives, where within the city might that be the most effective. So, okay, we'll go now into opportunity for mitigation. So I wanted to show some of the research here that synthesizes current machine learning and AI studies that are at the intersection of climate change and cities. And so that's this pie chart here on the right. This is from a study by Hsu et al. That has a preprint up. And so they've looked at different studies in the scientific literature that are focused on AI or machine learning and cities. And so you can see here in blue that most of the studies that they evaluated are actually focused on transport. And so a lot on shared bikes and scooters, on traffic management and routing, how consumers are utilizing some of these transportation technologies, micro-mobility, and then battery electrified transport. And then you can see the next topic is on buildings. So Philip will cover this area, so I won't go into that detail, but there are quite a number of studies that are focused on the application of AI for buildings. And then I was actually quite surprised that there's the green on urban form. So this is exactly going back to the IPCC's conclusion of not having a lot of data or information about what the impact is on spatial form and configuration. So perhaps a lot of researchers also read the IPCC and they said, oh, now we need to get a lot more research about spatial configuration and travel patterns and how urban form shapes consumption of energy and electricity, and also can lead to greater emissions. And then less on waste. So that was interesting in the poll. The first one, a lot of people said that that was an area where they were expecting that that was the greatest data need, and or the I guess like the most interest. And there actually has been very few studies. Actually, I wanted to give like a waste case study for this lecture, and actually I couldn't find really a whole lot on actual waste. And so you can see just a very few studies, and many of them are pretty localized to very specific cases. So it's kind of hard to find a study that does anything global or more generalizable. And then so that gives you a look at what researchers who are using AI are really focused on in terms of cities and the built environment. On the left is from a study by one of my PhD students, and she also did a big evidence synthesis, a big meta-analysis of literature related to just cities and climate change mitigation. And what she found is that in terms of effective responses, so this is a meta-analysis approach that looks at a bunch of different studies that try to measure the impact of different city level actions on climate change mitigation. So its ability to actually reduce emissions. So then she took all of those either measured or estimated effects and then ran a statistical model. And you can see that some of the most effective things that cities can do to reduce their impact on climate change and to actually tackle climate change mitigation would be things like clean energy generation. So increasing the amount of clean and renewable energy sources as part of their energy mix, or optimizing the energy system's operation. Transportation management is number 3. So I think it's good that there's a lot of now AI research that's focused on how we can also better manage transportation. Waste and wastewater treatment practices, it's interesting because it has the 4th largest effect size, but yet some of the very fewest, the very smallest in terms of actual AI related research. And then you can see here that actually a lot of these alternative transportation modes, which would include biking and shared bikes and these scooters, actually has the lowest effect sizes. But you can see here that 215 of the studies that Hsu et al. Evaluated actually focused on shared bikes and scooters. So I think this is an interesting disconnect, and I'm hoping that if folks are thinking about where to focus attention or what could be the most helpful for cities in terms of AI applications, I mean, I think we need to be really hitting some of these top 5 areas for mitigation to think about what might be the biggest bang for the buck in terms of how AI can really help cities access the broadest possible ability to reduce their emissions. So that's I just wanted to give this overview, and I know I wanted to leave some time for Q&A, and I'm quickly running out of time. So I just wanted to say that this type of synthesis and an AI-led synthesis is incredibly timely because the IPCC is now convening a special report specifically focused on cities and climate change. And so we just had the scoping meeting. So I was one of 6 US experts invited into this meeting in April to actually scope out what this report is actually going to look like. And the IPCC, in addition to having its big assessment reports that take about 5 to 7 years to write, they will often have these special reports in the interim. For this cycle, which is the 7th assessment cycle, there is only one report, special report, that has been authorized and is focused on cities. So that's incredibly exciting. So if you're thinking at all that you want to do something related to AI and climate change in cities, now is the time to do it because the IPCC relies on peer-reviewed scientific literature and studies. And so the deadline to get those studies in peer review, so it doesn't have to be accepted, it just has to be submitted into something peer-reviewed, is the end of 2025. So we still have some time to think about collaborations and studies because, as you saw, there are a lot of knowledge gaps. There's a lot of data gaps where I think AI can really help. And now is really the time to do that. So I would encourage everyone to really think about opportunities to inform this process because it's really critical to really try to get as much of the latest science and the best evidence to tell cities what they can do, what the possibility is, so that they can help in this fight against climate change. One of the areas that I've seen related to cities and climate change really take off in the last few years since the 5th or even the 6th assessment report was put together is really in large language models and generative AI. And I'm sure all of this is now quite familiar to you all through ChatGPT and all of these chatbots that have really put a face to AI. But a lot of the most recent AI applications that I've seen, particularly in my domain, is really using NLP and large language models to try to synthesize scientific evidence and to facilitate policy learning. And so a lot of these studies used unsupervised clustering techniques like topic modeling that, unlike a hand coding method where you might have like a code book and then you sift a bunch of policy documents or websites or tweets for certain themes, you let the model and you algorithmically then can identify these different themes. So in this study, we looked at more than 9,000 companies and cities and regional governments, as well as national governments, their climate action plans to just try to understand what are the areas in which they're focused on climate change. So this is a look at those 30 topics that we identified. And what is really interesting is you can see this light blue, this very tall bar, mostly only countries are focused on climate change adaptation. So in red, you do see that with some probability and frequency, you see that cities are tackling climate change adaptation, but mostly over here on the right, they're focused on mitigation. So looking at lighting in schools and buildings and building efficiency. So that's good news for Philip, but not as much focus on adaptation. And then I mentioned earlier that with this information about the emissions and then also with NLP and some of this topic modeling, we can actually develop statistical models to try to relate those two together. So cities are articulating particular strategies, you can see here, on buildings and spatial planning, or they're talking about a cross-sector approach between, let's say, air and waste and climate change, or if they're focused on energy efficiency or mobility and public transit and lighting, does that actually lead to their ability to reduce emissions? And what we found in terms of relating the plans with the outputs is that really energy efficiency is strongly statistically associated with European cities' ability to reduce emissions. So this just gives you a sense of what the utility of these topic modeling techniques might be for actually trying to understand and fill in some of these data gaps about what works in terms of policy impact and mitigation. And then, of course, I think with large language models, it's opening up the ability to ease policy learning and for cities and also companies and governments to better benchmark their own activities and to really understand what are best practices, what are other cities, what are other companies doing. And so we've actually also created our own chatbot called ChatNet Zero to try to ground generative AI to climate change expertise. Because the problem is if you go to ChatGPT or Gemini and you ask it a question like, can you continue to use fossil fuels and then pledge net zero, which implies decarbonization? Can you still do that credibly? GPT says, yes, you can. You can continue to use fossil fuels, which the IPCC and climate scientists say irrefutably, no, you cannot. You cannot continue to have a coal-fired power plant or continue to consume fossil fuels and still make a pledge to say, oh yeah, I'm going to decarbonize. My emissions are going to be net zero by 2050. And of course, the devil's in the details. The net part is always like quite confusing, going back to the example of offsets. And so we have a paper that we just published, the preprint. It's going to be presented next month at one of the computational social science workshops and the climate NLP workshop. So some of you hopefully will be there, and I hope to talk more with you about this paper. But what we actually found is that generic chatbots like GPT and Gemini, they tend to embellish a lot in their responses. So you can see in the red and the gray triangles, these are the average word or the number of words in a response, the average word length of the responses produced by Gemini and GPT. They tend to be much longer than the ones that we developed for these yellow squares for ChatNet Zero. And so even in our evaluation of the actual factual content of these responses, ours, because it was specifically trained on climate science documents and on specific data that we have evaluating different actors' net zero pledges, that it was much higher in accuracy than Gemini or Coral or GPT. And the embellishment ratio, particularly for GPT and Gemini, is quite high. So often these chatbots will say things like, Amazon and Walmart are becoming increasingly vocal when it comes to climate action, but there's no way to really verify that. And also that could mean that they're lobbying against more stringent climate action. So there's a lot of, I think, duality and a lot of concern that these generic chatbots could mislead through this hallucination or through this embellishment. So a lot more research needs to be done to make sure that large language models and NLP and generative AI can actually be a tool to help cities identify and benchmark their climate actions, as opposed to mislead them into thinking they can continue to use fossil fuels. So I only have a very few minutes to talk about climate change adaptation. So I'll just skip ahead to talk about the fact that cities are sites of inequality, and not everybody lives the same way within cities. And so here's two side-by-side maps of Atlanta, Georgia. So you can see income here on the left. So the most wealthy neighborhoods are here in the downtown area. And actually, it's interesting here because then some of the hottest areas actually happen to be the downtown area. But for a lot of cities in the US and throughout the world, it's not necessarily the case, where you actually find a lot of the hottest areas of a city actually overlap with low-income communities because they are located in more dense environments with high-rise buildings, and they don't have as much access to green space and tree cover. And so we actually found that pattern of disproportionate exposure in cities all across the US. So in triangles, these are cities where temperatures are higher for people of color, and it's the same pattern for people living below poverty. There's only like a few places like here in McNally, Texas, and a couple of other places where it's actually reversed, where they just don't have high percentages of minority populations. And the way that we have been evaluating and being able to make these assessments of disproportionate exposure to heat within cities is using satellite remote sensing data. And satellites, as you can see here on the left, are measuring land surface temperature. So the heat that's coming off of land surfaces or structures like rooftops or treetops or the ground. So actually the New York Times, they just did a study where they looked at 3 cities, and they used this land surface temperature data to say, in some sidewalks in Phoenix, it's 130 degrees Fahrenheit. And that's incredibly alarming. And I'm not discounting their methods, but also how many of you like live actually sleeping on the sidewalks? Probably not a whole lot of people. And when we use that data to then evaluate disparities, we can see here on the left for Philadelphia, it's a lot more varied. So the areas in red, we're talking about 45 degrees Celsius compared to the cooler parts in blue and green that are like 27 degrees. But then when we look at an alternate measure of temperature or heat stress, mean radiant temperature, you can see that it's a lot less pronounced in terms of the disparity. So that is another opportunity for, in particular, machine learning to try to develop more fine-grained and more human-relevant metrics of heat stress. And so that's what we did in this study here. We actually sent out a lot of students with these handheld sensors to collect high resolution air temperature and humidity data throughout an urban area. This is in Chapel Hill at 2 different times of day. And then we use machine learning to then combine other remote sensing inputs on land cover, on greenness, on built-up index, on land surface temperature. We also had high resolution aerial imagery that gave us a sense of building and urban fabric and form to then develop, you can see these much more continuous maps of heat stress. So this is infinitely more valuable for a city to be able to know for the entire city where there might be hotspots of heat and temperature that could then present people living in those areas increased risk and exposure of heat-related health impacts during heat waves. Already where I live here, I can't tell you the number of days. We've had at least 10 days, if not more, that have been high heat advisories. So heat indices, and I'm sorry, I don't know what this is in Celsius, but of over 106 degrees Fahrenheit. And that's also just pulling from data from weather stations that are often located at the airport. And again, I don't know how many of you live at the airport, although I know Philip's in Singapore and Changi Airport is amazing. So I would definitely live there, but most of us don't live at the airport. So that's not characterizing the full extent of temperatures that we may experience, not just from the air, but also from radiation coming off from buildings and from streets and other urban infrastructure. So that's, I think, another area for machine learning, and that's exactly what we're doing here. Hopefully you can see this really cool animation here on the left where you can actually see how this measure of radiation varies throughout a day. And this is developed from a very complicated microclimate modeling approach that my colleague Xiaozhang Li at University of Pennsylvania has developed. And so what we're now doing is we're trying to see if we can use machine learning to emulate this very computationally expensive and very resource intensive process of using this microclimate model called Solwig so that we can make it more accessible for policymakers and decision makers to replicate themselves. So a couple of months ago, we actually convened a bunch of local policymakers from various levels of government, and we showed them some of this data and what you could potentially do with it to better characterize heat risk, to develop adaptation and various heat mitigation responses. And they said, yes, absolutely, we want this data. And I did not think that they were going to say that. I thought they were going to say, no, we have enough data. But for those of you who answered risk, that's exactly what we heard from our local government counterparts, is that they actually need more data, particularly high resolution data. So this is basically like a meter spatial resolution. They said, absolutely, we want to have this data so that we know where we can actually develop adaptive or heat mitigation responses. That's exactly what the city of Raleigh did 2 years ago when they developed this. It's a very similar method to our citizen science approach where they put mobile monitors on top of cars and bicycles, and then people drove those across the city of Raleigh. And then they were able to identify these hotspots in red using a machine learning approach. And then here on the left, they immediately authorized $77,000 to then coat some of the hottest roadways in Raleigh with a reflective material to increase the reflectivity of these areas to immediately cool them down. So that's, I think, a really great example of how machine learning and AI can really help to identify these hotspots that can then immediately inform a response. But then the challenge of this was that it was only done for one day, July 23rd in 2021. And on that day, I remember it was like not even that hot because I helped out with this campaign. So you can see the temperature range was only 64 to 41, although in Chapel Hill, when we did our study, because I'm a mean professor, you can see some of the temperatures here in black were more than 108 degrees Fahrenheit that our volunteers were measuring. So this is not even like the extreme. And it doesn't even take into account this measure of radiation, which now we're trying to better capture through this modeling and machine learning approach. So I promised I would talk about some of the challenges. So I'll do that briefly, and hopefully I'll still have about 5 or 6 minutes left for questions. But also feel free to email me. I'll give you my email address, so feel free to email me. I think for cities in particular, the availability of underlying training data, I think, is a great challenge to really scaling the use of AI and machine learning in an urban context for climate. So going back to that map I showed you of all those cities that are doing things on climate change, and then the number that are actually reporting data, that's exactly indicative of the challenge. I want to take that model I showed you where I had that really nice map of EU city level emissions and emissions trajectory, and I want to expand that to the rest of the world. But I don't have access to solid city level emissions inventories from Latin America and the Caribbean, or from sub-Saharan Africa or Southeast Asia for that matter. So it could definitely bias the training of any type of global model if most of the data is being pulled from the EU. So I think that's a real challenge, that machine learning and AI, it's definitely not a silver bullet, and it's not a cure-all for all of these data challenges that cities face, because at the end of the day, you still need to have very solid and representative training data to have confidence in those results. And that really matters for cities. I think transparency and trust of data and AI models is paramount. Even when I show cities their own data that I've collected, the first question they ask me is, where did you get that data? How can I trust that data? And even when I tell them, this is your own data, like I gathered this from your Environmental Protection Bureau or from your monitoring center, they still don't believe me. They're like, oh no, we'll need to have our engineers or our technicians look at this, even when it's their own data. So cities are incredibly skeptical when you show them any data that is not theirs. And that's a huge challenge. And I think really making AI and machine learning meaningful for cities to tackle climate change. So as an academic, we can do whatever scientific studies that we want. But I think also for the charge of the IPCC and the special report on cities, we have to think about how cities are going to receive it and what information needs do they have, what questions do they have, and then how can we work together with them? They have to be involved in the process. I think that's really important, this process of co-production and co-creation, because machine learning and AI is already a black box. And so if it's a black box to a lot of people who use it, I mean, including myself, I'm saying me too. Imagine if you're a non-expert or you're a practitioner or a policymaker, how much more obscure and obtuse those processes really are. So I think that's really, really important. And I think that also goes back to the capacity and the analytical capacity of cities when it comes to AI and even using data to make decisions. I think we take it as a given and take it for granted. But in a lot of my own research, we find that the analytical capacity, do they have like a person who understands GIS? Do they have a person who understands machine learning or who can code in Python? Because if the answers are yes, then I think just scales the possibility of the uptake of machine learning and AI approaches in that use context. So we actually invited a lot of the data people from cities into our meeting alongside the government people who make the decisions and the plans. And that was really valuable to have somebody, because then they can go back and say, oh yeah, her model is legit, or they need data for this, or this is how we can use the model, and translate it in that context. And then I think the last point is an area that I'm sure will come up in every single lecture during this lecture series, which is Jevons paradox. I think there's a lot of concern, particularly on large language models and Gen AI, is that as more and more cities are using these tools, or researchers are using these tools, it could increase energy consumption in Jevons paradox. So the more we use these tools, that could increase the climate and energy footprint of cities. So how can we make that balance, or make sure at least the electricity is from clean and renewable sources? So I vastly overwent my time, and I apologize, but I'm hoping we have a few seconds or a few minutes for questions. So thank you so much.
Yeah, thank you so much, Dr. Hsu. Your presentation is very impactful and very informative, especially from a big picture at a large scale, such as cities. And it's really interesting, at least for me. And there are a couple of questions from the audience, and but I'll pick up some from them. The first question is, can some of the techniques used in biodiversity can be used in city studies?
Yeah, that's a great question. Should I just go ahead and answer? Or do you want me to try to answer all of them? I can see them in the Q&A.
Yes, please, if you can answer them in a quick
Okay,
short
great.
time period.
Yeah, and I'm also happy to follow up with folks. So if the folks who ask these questions would like to email me, I'm more than happy to also email. To respond to Jerry's question about techniques used in biodiversity and city studies, yes, absolutely. I'm actually finishing a paper right now where we're using fragmentation metrics. So you may have heard of frag stacks that look at the patch size of in terms of biodiversity studies, they're looking at habitats and habitat fragmentation, and that relates to species. And we're using that to actually evaluate changes in patterns of green space in redline cities in the United States and how that relates to temperature change. So yes, I think absolutely there's a lot of potential there. And then Jerry also asked, are there studies on future human migration due to climate change? Yes, that is an active area of research. There was a great meta-analysis on this in Nature Climate Change a couple years ago. I can't remember the lead author of this, but I'll try to find it and send it to you if you can send me your email. And yeah, definitely that's a very active area. but it's also very difficult to measure. Actually, there's a PhD student in our department who's actually looking at climate-induced migration as well. So yeah, I'd be happy to follow up. And then Nirzari asked, how can behavior change among city residents globally be nudged towards reduction of emissions, be it reduction of plastic usage, synthetic clothing, fossil fuels, hyperlocal deliveries? I 100% agree. I think that in the climate scientific literature, this is called the behavioral wedge. So we can think about reducing emissions in terms of different technologies and wedges. And this demand side, or the consumption, is like the one wedge that is now, I think, receiving a lot of attention. And in the IPCC, the Working Group 3, Chapter 5 was the first time they actually included a chapter on demand. So not just looking at supply side responses like clean and renewable electricity or transport shifting. It's actually about behavior and consumption. So I think that that's so critical, and I think requires a lot of interdisciplinary collaboration to try to nudge behavior. But that's like a really challenging question. Do I have time to talk about the last two, or I don't want to cut into Philip's time because I know it's also going to be late in Singapore.
Because it's already running out of
Yes, yeah.
Yeah. So for the audience, if you have any questions, you can email to Dr. Hsu, yeah, for more discussion.
Yes, please. Thank you. Thank you so much. Really appreciate it.
Thank you so much. Okay, so now we're gonna move to the second lecture called AI for Buildings and Cities. The speaker is Professor Filip Biljecki. So Dr. Filip Biljecki is an assistant professor at the National University of Singapore and the founder of the NUS Urban Analytics Lab. His research and teaching are converging geometric engineering, geospatial technologies, and urban data science to support digital twins and data-driven urban planning. He has published more than 100 peer-reviewed articles. So welcome, Dr. Filip Biljecki, for giving us a presentation. Yes, please.
All right, hello, I'll share my slides.
Sure, go ahead, please.
Okay, do you see my slides?
Yeah.
Okay, thanks a lot for having me here. It's really nice to give this presentation after the really nice talk by Angel. So I'm Filip Biljecki, and I'm an assistant professor at the National University of Singapore, where I have established a research group called the Urban Analytics Lab. And most of my group are geospatial engineers, but together with a few other research groups here at NUS, we are converging towards the building scale. So in the next 45 minutes, I'd like to give you an overview about how we use AI for buildings and cities. So my presentation will focus both on the city scale and building scale. I'll try to bridge between Angel's presentation and the tutorials that come later. So after this presentation, there will be a couple of tutorials like CityLearn and a tutorial on building control. So in our work and in general, the community has identified some challenges and opportunities that we are working on. They are primarily understanding emerging data. So today, as the urban environments are becoming more complex, we need to explore further data sources, and there is a great research opportunity in that. Next, a lot of data sets nowadays have issues with gaps and data quality. This topic was a bit covered also by Angel previously, and overall there is a consensus that we need better data, and this is of course becoming more and more relevant now that AI is gaining more and more traction. Then as built environments are becoming more complex and data is coming from all different sources that are across different scales, we need to focus more on multi-scale integration of data. And finally, a lot of research is focused on the built environment, but not really on the human aspect. So we think that we need to bring humans in this loop. So my goals in this presentation is to raise awareness of emerging forms of data, primarily geospatial data and their quality. I'd also like to use this chance to present different use cases that are relevant for climate change mitigation and adaptation from our research group, but also our sister research groups with which we collaborate. And next, I'd like to give you some examples of what I mean when I say human-centric AI. So applications and use cases that put humans in focus. And also like to share some ideas about research directions. So this research that I'm going to talk about is not only conducted at my group, but we are blessed to work with other research groups here at NUS. One of them is the Building and Urban Data Science Lab, and another one is the BEAM team. And I'll be mostly talking about this through specific examples, and I'll be talking about also the data needed for urban climate change action. So one of these examples of emerging data sets that we are exploring is Street View imagery. So this is one of the recently emerging data sets that can support research that is of relevance to climate change, for example, for characterizing the urban form in cities and characterizing also the building form. So I think most of you are aware of Google Street View. Google Street View has achieved tremendous progress in the last decade, thanks to the efforts of the company. So they collected dozens of billions of images that look like this across thousands of cities around the world. And this data has been used for several purposes in academia. For example, researchers have used it for understanding human perception, understanding infrastructure. For example, Street View imagery has been used to map certain elements in the built environment that is not visible from traditional geospatial data sources like satellite imagery. Street View imagery has also been used to map human activities. And most importantly, for this context, it has been used to map the urban form. So thanks to different AI techniques like image segmentation, researchers have been using Street View imagery, not only from sources like Google Street View, but also in China, sources like Baidu Maps or crowdsourced SVI sources like Mapillary to identify the proportions of greenery in an image to understand what is the amount of greenery at the street level, then proportion of visible buildings, and also proportion of visible sky. So thousands of images across the city have been used, have been coupled with AI techniques like image segmentation to calculate all these elements that have been aggregated at a city scale to create data sets that characterize the urban form and can be used for climate change related downstream analysis, like understanding the association between the built form and the urban heat island effect. So Street View imagery has been one of the most important emerging geospatial datasets recently, both in practice and academia. Another application that has been emerging thanks to Street View imagery and different computer vision techniques has been change detection. And this is quite important for climate change adaptation and mitigation, because due to climate change, the built environment is changing and we need to track these changes. Traditionally, satellite imagery has been used to monitor changes in the built environment, but as I have indicated earlier, satellite imagery is often not sufficient to capture these changes because there are lots of elements in the built environment for which Street View imagery may be more suitable. So in our group and in other research groups around the world, Street View imagery has lately been used to detect and map changes, like changes in the sky view factor at a very high spatial resolution and changes in the amount of visible greenery from the pedestrian point of view. So Street View imagery is not the only exciting data set that has been emerging that can support this kind of research, but also crowdsourced forms of geoinformation or user-generated geographic information like OpenStreetMap. They have also been growing in popularity and content in the last few years. So OpenStreetMap is probably the best example of that. OpenStreetMap is an open platform for mapping that has global coverage. For example, this is a screenshot from OpenStreetMap that shows a part of the campus here at the National University of Singapore. And OpenStreetMap has been quite useful in the last several years for different kinds of research because it often includes detailed geospatial data at the district scale and at the building scale of many different features beyond buildings as well. For example, green surfaces, amenities, roads, pedestrian paths, and so on. And nowadays, it's quite exciting because OpenStreetMap contains more than 600 million buildings mapped. And for that reason, OpenStreetMap has been supporting a lot of research on the urban form and other relevant applications at the city and building scales that are relevant for climate change action, detection, and mitigation. So for those of you who have not experienced, who don't have experience in urban form research, basically researchers in the last decades have been developing means to quantify the urban form. So they have been developing metrics to quantify how cities and buildings are built and designed. For example, site coverage, average complexity of buildings in a neighborhood, average height of buildings in a district, and so on. And that brings me to another example of research that we have published in 2022. It's called the Global Building Morphology Indicators, which is one of our open projects that focuses on three problems. First, it introduces a catalog of metrics that characterize urban form. Second, it introduces an open source tool to compute these metrics. And third, it releases an open data set that characterizes the built form across dozens of cities around the world. So to give you an example of this data set, here is a map of Singapore that is partitioned in cells of size 100 by 100 meters, where for each cell we have computed what is the average distance between buildings. And the darker the colors are, these cells indicate locations where buildings are closer to each other, while the brighter locations indicate those areas in Singapore where buildings are more far apart from each other. So this data sets, and by the way, this is only one of 600 metrics that we have computed, can be coupled with different AI techniques to understand different urban phenomena like the urban heat island effect. Because researchers have found, for example, that there is a direct association between some of these metrics and the urban heat island effect. So this project is completely open. We have released the paper openly, we have released the code openly, and also the dataset. So it presents an off-the-shelf solution for urban researchers, especially those working in urban climate, to support their work. But going back to the data, so this is the example of OpenStreetMap in Singapore that I have shown, but you may wonder, what about the quality of this data? Unfortunately, the quality of these emerging data sets, primarily OpenStreetMap, is not always perfect. And that hinders a lot of research in many locations around the world. Here is a less optimistic example. It is a screenshot from OpenStreetMap in Indonesia, in one town on the island Java, in which you can see that in which you can see an example of asymmetric situation in which we have roads mapped, but we don't have buildings mapped, meaning that we cannot really use this data everywhere because we have a bunch of data gaps preventing us to conduct lots of different analyses like urban morphology. And can we use AI to improve this kind of data? So that brings me to another example of research in which we have employed AI techniques to help to try to improve the data quality and fill the data gaps in order to support research studies that are critical for understanding climate change, for example, urban form computations. So in this research called GenMapper, we have introduced a new way to fill gaps in datasets on buildings, which are critical for urban form studies. So we built an approach using GAN to take data of other spatial features that are usually complete, like street networks or land use, to predict building footprints. So basically, GenMapper takes the left as input, so a street network, and it generates what you see on the right, a city-scale data set on buildings that contains their 2D geometry. We tested GenMapper across many different land uses and urban morphologies around the world. And on this slide, you can see an example for 4 cities that have completely different urban morphologies like Seattle, Frankfurt, Jakarta, and Rotterdam. In the left column, you can see an example of the input data we have used for GenMapper, while in the center column, you can see an example of what GenMapper has generated, while on the right, you can observe the ground truth, so how these building footprints actually look like. So this is the first such application of GAN, which has been quite a popular AI technique to fill data gaps of buildings at the city scale. And as you can observe from this example, GenMapper is not 100% accurate, but it can help us to approximately infer the urban form in cities. So we can roughly tell how many buildings there are in a neighborhood. We can roughly estimate what is their shape and size. and we can achieve an accuracy that is sufficient to conduct lots of relevant downstream analysis, like computing the urban form matrix. Going back to the topic of quality, we have then been looking into how can we actually use GenMapper to detect data gaps in the first place. So one issue with geospatial data at a large scale, which is growingly used in climate change studies, is that actually we don't really know where are these data gaps, because if you see there is a location in a city or beyond a city where there are no buildings mapped, this is not necessarily a data gap. It is possible that this location simply doesn't have any buildings mapped in reality. However, there are no automated means to automatically determine whether a district or a certain area doesn't have buildings because it's a data gap or simply because there are no buildings there. So we have used GenMapper for precisely this purpose. We have been isolating these portions of space that don't have any buildings mapped, and then we have used GenMapper to assess the completeness of buildings. So we have used GenMapper to predict how many buildings are supposed to be there based on the street network, and then comparing how many buildings are actually mapped there in that area in OpenStreetMap. And then if there was a huge mismatch, we have been identifying these areas as data gaps. So here is an example of Seattle, in which we have automatically determined which of these districts have issues with data quality. However, for lots of relevant studies like energy modeling, which you will also hear about later in the tutorials, building geometries are not the only relevant geospatial data sets. Also, semantic information about buildings is critical as well. So understanding how tall a building is, so how many floors it has, what kind of building it is, meaning the building function, and aspects like material of the building. And this data, as you have seen on the previous slide, is also available in OpenStreetMap, but its quality has not been really questioned. So lots of researchers, they download data from OpenStreetMap, data that contains the type of the building, the number of floors, and researchers have typically used this data without questioning what is actually the quality. So that prompted us to conduct the first global quality analysis of this kind of data. We focus on two aspects of data quality. One is completeness, so understanding what kind of semantic attributes there are in the data set, how frequent they are, and second, we focus on their accuracy. So we look into these more than 600 million buildings in OpenStreetMap, and we found that there are more than 22,000 unique attributes that contributors typically record. But out of these 22,000, actually only a few, like building type, are actually predominant around the world. Globally, we found that completeness of these attributes is quite heterogeneous, but overall, less than 20% of buildings have information about their type and the number of floors. Then we looked at the city and district scales, and we found that completeness at the district scale goes from 0 to 100%. So while the global completeness is less than a fifth, so only every fifth building has attributes recorded. Actually, if you look at the completeness at the district or city scale, the situation is quite heterogeneous. So in lots of cities, there are districts that have this information available for 100% of buildings, while in some other district that is almost literally next door, there are almost no buildings that contain these attributes. So understanding data quality and aspects like data completeness is critical for these studies. But unfortunately, we found that in practice, researchers tend to take this data for granted. So there are definitely data gaps in this kind of data, but also we found that there are inaccuracies. Because if a piece of data is there, it doesn't mean it's accurate. So if we have for a certain building available information like the building type or the number of stories, that piece of information is not necessarily accurate just because it's there. So in the next phase of this research, we have focused on the accuracy of this data. So we manually sampled thousands of buildings around the world, and we found corresponding street view imagery from which we can visually infer these building characteristics. And we found that in most cases, this information is accurate, but it's not 100% accurate. So we found that for, say, for example, 72% of buildings, the information about the number of stories is accurate, while for the rest is inaccurate. So this kind of attributes have been critical for lots of urban scale and building scale studies pertaining to climate change. However, the situation you see on the left, so a data set in which we have the type of building available, the number of floors available, the address, and so on, is actually not as common as the actual content of the data, the example on the right, in which we have only the geometry of the building available without any semantic information whatsoever. So in practice, in lots of districts, we have the situation on the left. However, for most of the buildings in most districts around the world, unfortunately, we have no semantic information available, preventing lots of studies that are quite important for climate change action and mitigation. So then we have been looking into how can we use AI to improve this data on buildings. In the previous example, I have shown you an application of using AI to fill data gaps in terms of building footprints. So I have shown you how we used GAN to predict the geometry of buildings in a city. But then in the next research, we have continued this work, understanding how can we use AI to fill data gaps of semantic information, so attributes of buildings. And for that, we have been looking into another instance of emerging geospatial data, and that is real estate ads. So almost all countries and real estate markets around the world, they have websites that are they have online marketplaces in which people advertise their real estate properties for sale or rent. And we have then been looking into, can we make use of this data of these websites to fill data gaps about buildings? Because when people sell apartments or houses, they typically tend to also describe some information about buildings that are critical for use cases like energy simulations, which you will hear later in the tutorials, like number of floors, type of the building, year of construction, and so on. So in this paper that we publish in Urban Informatics, we have developed a completely new way to acquire building information and thereby filling data gap on building information across cities and districts around the world. So we have wrote a scraper that scrapes continuously real estate ads, and then use AI techniques like natural language processing and computer vision to extract information that is relevant at the district and city scale to support downstream analysis. In this research, we have employed also computer vision because ads on real estate, they don't only contain data, they don't only contain textual data, but they also contain pictures. And then we have employed computer vision to extract relevant information from images as well, and then use that to fill data gaps to obtain information about buildings that is usually not available in geospatial datasets like year of construction, number of floors, type of building. But also in this research, we went a step further and we also mapped amenities that are associated with buildings like swimming pools, gyms, and so on, because they're also mentioned in real estate ads. So when we have good data, then we can also develop some new use cases. And I want to show you some examples of use cases that have been enabled thanks to recent AI developments and use cases that are relevant for the topic of this summer school. So I'd like to focus on rooftops, which have been quite important for urban sustainability. So rooftops have been in focus on the planning and urban sustainability community for many years because they offer a lot of underutilized space that can be used for purposes like installing solar panels to collect solar energy. They have also been used in some places to for greenery and even growing food. So all these three examples are from Singapore. And in the past decade, researchers have been focusing on mapping the potential of these rooftops. For example, they have been focusing on developing workflows. Some of them include AI to identify what are the best locations for, say, installing a solar panel. Other researchers have also been focusing on quantifying this potential at a large scale. So they have been quantifying and predicting how much energy can we produce if we install solar panels on half of the rooftops in a city or country. And we have been following this kind of research with great enthusiasm. And this kind of research helps us to understand what is the potential of these rooftops in the future for different typologies of roofs, like those that contain solar panels. But we notice an important gap is that if you start asking these researchers or government officials, but what is actually the current situation and actual status of rooftops at the moment? What is actually the current utilization rate? How many rooftops at the moment actually have solar panels installed on them? Unfortunately, these are answers. These are questions that don't have answers because a lot of this research has been focusing only on the potential in the future, not really what is the situation at the moment. For that reason, we have developed Roofpedia, which is a project in which we heavily rely on AI and geospatial data to map the content of rooftops. So instead of focusing on the potential of rooftops, we wanted to focus on the actual situation now, understanding what is currently on the rooftops, because only then we can talk about the potential. And in this project, we mapped 1 million rooftops across 20 cities around the world to understand how many of them already have solar panels and how many of them are already green. So this is an example for Singapore. We have detected using techniques like image segmentation, computer vision, which buildings already have solar panels on rooftops and put them on a map. This is a paper that was published in Landscape and Urban Planning. The workflow has been quite straightforward. We have used high-resolution satellite imagery. We have built a computer vision model that is focused on two objects, solar panels and greenery. And then wherever a rooftop was detected to have some of these features, we have enriched data on buildings. And because we do this at the city scale, we can understand what is the spatial distribution of these rooftops that have either greenery or solar panels. And next, because we do this for multiple cities, this enables us to conduct comparative analysis across cities to understand how successful cities are when it comes to unlocking the space provided by rooftops. And by extension, in a way, to understand how cities are sustainable when it comes to rooftops. So far in my lecture, I've been talking a lot about the built environment, matters like greenery in cities, solar panels, sky view factor. But one gap in research like this are humans. So humans are typically not in the focus. And then we decided to focus more on humans. And we started working with another research group here at NUS called Buzz Lab, which has been developing a platform called Cozy, which is an iOS application that works on Apple Watches that focuses on deploying surveys and collecting physiological data on people. So Cozy is an app that allows you to deploy microsurveys to sense the comfort and context of people. In their project so far, they have been mostly focusing on the thermal comfort. So they've been using this app to collect physiological data. They've been using this app to collect physiological data on people, but also deploy these so-called microsurveys. And they're called microsurveys because they are very quick surveys that allow them to understand how people feel at the moment. For example, do they feel warm? Is the temperature comfortable? Or do they feel cold? And these surveys have enabled them to understand how people feel inside buildings. So what you see here is a collection of data points where each point indicates by color how people felt at that location in a particular period. And this kind of research, collecting data on humans coupled with AI techniques, help them to understand how people feel in different spaces of buildings. In these studies, they found that different people have different preferences for the thermal comfort. So some people in the same room, they would feel cold, while for a subset of other people, the temperature is perfect. It's comfortable. So in the next phase of the research, they've been developing comfort models based on unsupervised machine learning to identify different phenotypes of people or different personality types with respect to comfort. And they identify different clusters of people that have different preferences. And this kind of research will help us to design spaces within buildings that are suited for different kinds of people. For example, some people may prefer temperatures in indoor environments that is very cool, while others will prefer warmer areas. So these kind of comfort models help us to understand not only the personality types of the different people in the built environment, but also how to design a space that are suited for these kind of personality types. Then we really like this research line, and we coupled with them to think beyond the thermal comfort and think beyond buildings. So comfort is actually much more than thermal comfort. Visual comfort is also important. Also, there are aspects in the built environment that affect comfort, like not only what people see, not only how they feel, but also what they hear. And comfort in general in the built environment is influenced by lots of different factors. And we went beyond buildings in this research and started deploying watch surveys at the district scale to understand what are the aspects that influence comfort in cities. So we have been recording not only the temperature where people move, but also what they see using street view imagery and what they hear. And then we develop a graph neural network, another deep learning technique, to help us to explain how are people influenced based on different factors in the built environment and based on the data collected from watches. So this kind of research helps us to understand how different people are influenced by different aspects in the built environment, and how can we build better streetscapes that will help us mitigate climate change. Our current work that also includes the development of certain AI techniques is focused on developing the so-called GTI, or just-in-time adaptive intervention messages, that learns about people and helps them send a notification to intervene and change their behavior to make them more comfortable. For example, one application we are working on is send notifications to people who are in rooms in buildings that don't suit their preferences. So the idea is to learn about people using AI techniques and then find spaces that are more suitable for them. For example, say a person goes to a room that is warm, but we know from their preferences that they prefer cooler areas. Then we are sending a notification to that person saying, hey, if you go one floor up, there is a room that should be more comfortable to you. So this is being developed for indoor, but also outdoor at the city scale. We are looking into driving people to go to indoor areas when it's too hot, or have them go to parks in case we detect discomfort. We have been collecting lots of data about this, not only at the building scale, but also city scale. And we have also released this data openly. So we just released a Kaggle competition. Anyone can download this data and develop their AI models that will help us understand comfort in cities. So I'm almost done with my lecture. You have seen by now that we are working with different research groups using different kinds of data that come in different shapes and flavors and also different scales. So one research direction and one challenge and opportunity that we have identified is how to put all this data together, how to integrate all these different scales. And we have been developing a digital twin here in the campus that I want to show you that attempts to put all this data together in a single platform that will then help us drive analysis in a single integrated manner. So this video shows the data that was collected from a watch, a person moving in the campus along a particular route. And on the right side, you can see the data which we collected. So what people see, how they feel, and also the surrounding context like the temperature. So I hope that this mix of different topics from data quality, data gaps to use cases all under the umbrella of urban sustainability and use cases that are relevant for climate change mitigation help us to help you to make sense of the recent challenges, opportunities, and future directions. And I'd like to conclude this presentation with a few takeaways and lessons learned in the last few years and how we see this kind of research line moving forward. First is about emerging data sources. So we think that they can help us gather further insights in the built environment. As built environments are facing increasing challenges and are becoming more complex, we need new kinds of data to help us gain more insights. And some of these data can be crowdsourced, and we think that in the future they will grow in importance and availability. Second, as AI techniques become more popular and as more and more data becomes available across different sources, across different scales, we shouldn't really take this data for granted, but we should increasingly question their quality. So this is not a new topic, but it has kind of been taking the backseat, and we think it deserves more attention. Third, integration of data is quite challenging, but it is increasingly important, and I think this is a viable research direction in the future. And finally, humans are quite important in this picture. So human-centric AI is becoming more and more important. We should be collecting more and more data about people and developing personalized AI models. So I've taken exactly 45 minutes. I'm on schedule, so that leaves an opportunity for questions and discussion. I'll be happy to discuss further. Thanks a lot for being here, for having me here, and for your attention.
Yeah, thank you, Dr. Filip. Thanks for this wonderful and amazing presentation. So we have a couple of questions. The first one is to ask, can you assign energy consumption or CO2 emission to urban morphology?
Yes, technically yes, but I have not seen lots of examples in practice. So it is possible to estimate energy consumption thanks to urban form data and associate it or integrate it in data on buildings. But these examples are not so common in the city scale, they're more common on the building scale. And I believe that in the tutorial that comes afterwards, you will see specific examples of that.
And the second question is that the audience wondering if you can use insurance data to fill in the data gap.
Oh, that's a really interesting question. I have never really thought about this. Technically, yes, but I'm not aware of any openly available source of insurance data. So I think only insurance companies would be able to do this. Yes, I don't know much about insurance, but this is definitely an interesting idea. I believe should be possible, but this kind of data is not available openly, so we as a research group at the university cannot do much about this.
Okay. And some people are wondering, because Singapore is one of the most highly developed cities in the world, will this AI mapping of cities work for less developed and planned cities in other emerging countries?
Yeah, absolutely. Thank you for this question. I'm glad it was brought up because even though we are a research group based in Singapore, our focus is also the rest of Southeast Asia. And different cities and countries in Southeast Asia have different levels of development. And we found that lots of the research we are developing can also be applied in less developed places. So there is absolutely it's absolutely possible to apply lots of these use cases in less developed cities and countries in around the world. I can give before we move to the next question, just to continue with this one. I can give you a specific example, like Roofpedia. Roofpedia, the project for mapping solar panels, it relies on high-resolution satellite imagery. And this data is actually available not only for the highly developed cities, but it's also available around the world for a variety of cities.
Sure. And the next question is asked because the effect of developing AI in terms of comfort will contribute more, if it will contribute more to climate change, since the training and the inference of AI models would use the energy.
Yeah, that is true. I believe Angel before me talked about this aspect. Yeah, technically this is definitely true.
Mm-hmm.
I don't know exactly. I cannot really quantify how much would the impact be, but that has been a growing concern in the AI community lately. So the answer is yes, I guess. It's an important consideration. I'm glad it was brought up.
Okay, thank you. And one more question. Can building data be used for vulnerability assessment?
Yes, in fact, data on buildings is used for vulnerability assessment quite often. One example that comes on top of my head is earthquake risk. So researchers have quantified the risk, the exposure of buildings to earthquakes, and predicted how damaged would they be in certain scenarios. Also, in terms of vulnerability assessment, there have been applications related to floods, understanding how in different flooding scenarios buildings would be affected. For example, how many buildings would be damaged, but also by extension, how many residents would be affected by floods. So the answer is absolutely yes. Vulnerability assessment has been one of the main use cases for building data.
Okay. So that's all questions from audience. Thank you so much, Dr. Filip, for your wonderful presentation, and your research is really interesting, and some of the figures, they are very fancy and they are informative, especially I think because my background is the building energy prediction, especially at urban scale. So the data set you generated at least very useful for my research. Yeah, so thank you so much.
I'm glad to hear that. Thank you for having me and for organizing this summer school.
Sure, okay. And I already sent the feedback form link. So for the audience, could you please also fill in the form to give us your feedback for these 2 lectures on day 9. So thanks everyone. Thanks for your participation in today's day 9 lectures about AI on buildings and cities. So yeah, that's it for today's lecture. Thank you very much. Have a great day.
Thank you. Have a great day.